This is the next video of solutions for the optimization homework. And this is that Unit 6 section day 4 till 7. So this is the second set of questions from the page 152. So our first one here says, a sociologist determines that a foreign language student has learned n at t equals 20t minus t squared vocabulary terms after t hours of uninterrupted study. So we're looking for C. If we're talking about rate, remember rate here, that's always the rate of change is always the derivative. So for B, we would be looking at M prime. So we're going to need that to find where this is. So that's 20 minus 2t. And if we think about the maximum rate in terms per hour, the maximum would happen, and this is for C, would be where the derivative of that function would be equal to 0. That could be a max or it could be a min. We're going to have to kind of check that out. So here we've got 20 minus 2t equals 0. So if we solve that, we get t equals 10. Now we want to kind of specify, like, do we know that that 10 is a maximum? Because we don't have our endpoints. Like if it said t was between like 0 and 20 or something, that there was some amount of hours, but we're not given that. We don't actually know that there's specified endpoints here to the time that we're allowed. So I am going to say that t has to be positive because really that's pretty straightforward in terms of time. And I'm going to look at this two ways. I'm going to look at it as a chart. So what's happening to the derivative between 0 and 10, and then after 10. And then I'll also kind of look at this as a graph of my derivative. So if I look at this as a graph, then I know that the graph of the derivative is going to be a line with a slope of -2 and a y-intercept of 20. So it's going to be a line, I don't know, kind of like that this would be there. So I know that this is going from a positive rate of change, because the y values are positive there, to a negative rate of change. We can also look at that in terms of the equation, just sort of by substituting in a number between 0 and 10. If you put in 5 for t, you're going to get a positive value there. And if you put in a number bigger than 10, like if you put in 20 in there, 20 minus 2 times 20, that will be negative. So then it goes to negative. So what that tells us about the function is that it's increasing. It's got a positive slope before 10 and a negative slope after 10. So we know that it's increasing until 10 and then decreasing, so that must be the maximum. Okay, so therefore the maximum rate is n prime at 10, which we would, so the maximum rate is at 10 hours. And the next one, Sandy's making a closed rectangular jewelry box with a square base from 2 different woods. The wood for the top and bottom costs $20 per meter squared, and the wood for the sides costs $30 per meter squared. So we're going to have some kind of measurement here. And it says that it's a square base, so I'm going to make the base x, and then an h for the height. So we want to minimize the cost. So remember, we always want to come up with the function for this, even if it's in terms of a lot of variables, like more variables than we have, that's okay. So we want to have a minimum cost. So I might even just kind of write this out as $20 times the area of top and bottom plus $30 times the area of the sides. And we'll just kind of write it out like that, that's going to be my general equation of what I'm going to find. So the area of the top and bottom would be x squared, and then the bottom also is x squared, and then each of the four sides would be xh times 4. So here we'd have $20 times the 2x squareds, for one for the top and one for the bottom, plus $30 times 4 xh's. Like that. So I can simplify this a little bit. 40x squared plus 120xh. Now, what I really want to do is figure out one variable for this equation. So here I need to have, probably want to get rid of your h. And it tells us we have to have a volume of 4,000 centimeters cubed. And what might be the difficult part in this one, I'm just realizing now that because this is in meters squared and this is in centimeters cubed, we're going to have to adjust that. And we'll have to kind of think about what this is. I've already kept this in meters squared, so I'm going to keep that. And I want to figure out 4,000 centimeters cubed. How many meters cubed is that? Okay, so the trick here is that we know meters to, or centimeters to meters, that we would multiply by 100, right? We know that you multiply by 100 to convert from meters to centimeters. So there's 100 centimeters in a meter. If you were converting 4,000 centimeters into meters, you divide by 100, right? Going from centimeters to meters. If it was centimeters squared to meters squared, you've got two dimensions there. And if you can imagine just kind of picturing like a centimeter squared, if you had a full meter and you had like 100 centimeters here, and then you marked that off, like 1 meter squared is a big area, right? Like imagine a piece of paper that was a meter by a meter. That would be quite big. It's like the size of almost a whiteboard or something. And if you imagine 1 centimeter squared, that's like a teeny tiny little piece. So it would be 100 and 100 both ways. So 1 meter squared is actually 100 times 100, or 10,000 centimeters squared. So you would have to divide not by 100, but by 100 squared, or 10,000. And then sort of similarly, if you were going from centimeters cubed to meters cubed, you would have to divide by 100 cubed. So that's what I'm going to do there. 4,000 divided by 100 cubed. So that would be 0. I want to get my decimals right. 20004 meters cubed. So 4,000 Centimeters cubed sounds like a lot, but if you can kind of imagine those like wee little centimeter cubes that you maybe use for counters in elementary school, or like used to practice measurements with, like a centimeter cubed is a pretty small amount. Now, if you imagined a box that was 1 meter by 1 meter by 1 meter, that's big. You could probably fit in that box. If you put 4,000 of those little cubes in, it wouldn't make much of a dent. Like, it's not going to be close to 1 meter cubed. It's quite a small amount. So that's what I'm going to use as my total volume. So I know that volume would be the base, area of the base times the height. So 0.04 equals x squared h, and then h equals 0.04 x to the negative 2. Again, I'm not putting over x squared because I know I'm going to have to take the derivative. Then when I sub that into my cost function, 40x squared plus 120x times 0.04, oops, more zeros in there, 2 zeros, 0.004 x to the negative 2. So then C is 40x squared plus 0.48 when I multiply the 0.004 times 120, x to the negative 1. So then the derivative of that would be 80x minus 0.48 x to the negative 2. So I'm going to look where C prime would be 0. So 0.48 over x squared equals 80x. 0.48 equals 80x cubed. So that's 0.006. And x would be about so x there is 0.18 approximately. So we could do the comparison here. We could talk about what like reasonable bounds would be to try and figure out where this was increasing or where it was decreasing. I'm going to try and squeeze that in a little bit here. So if x was 0.18 meters, that would be 18 centimeters. So you could do the check and take a look where that was increasing and where it was decreasing. And kind of look at the sign and just kind of confirm that that would be the minimum cost. So as you can see, if I put in values in there, that we would get a negative if I substituted in a number less than this. So you could just do maybe like 0.1, and you'd put that in to your derivative just to double check that you did get a negative answer. And then any number bigger, like if I put in x equals 1, you're going to get a positive in there. So it's decreasing. The function is decreasing because the derivative is negative. Then it's increasing. So that is our minimum. So make sure you put a therefore. So minimum cost is x equals 18 centimeters. And I believe that we can figure out what the height is. That 18 times 18 is 324. So then we do the 4,000 volume divided by that, and it's about 12.3 centimeters. If you sub that back in just to figure out what your H would be. Okay, the next one, we have a basketball team that plays in an arena that holds 20,000 spectators. Now that's actually kind of interesting. We haven't had a lot where we've got an upper bound. So we can figure out what the capacity is for this arena. So average attendance has been 14,000. The average ticket price is $75. Market research shows that for each $5 reduction in price, attendance increases by 800. Find the price that will maximize revenue. So this is very, very similar to your like grade 10 quadratics. We know that the revenue is the price times the number sold. So the price that you're charging times how many. And just like in grade 10, I'm going to say let X be the number of $5 price reductions. Okay, so I know that the price is going to be the $75 starting price minus 5x, because you're reducing the price by $5 x times. And the number that you sell, the number of tickets sold, will be the 14,000 that they normally do, plus 800x. You're selling 800 more tickets each time. So this is just going to be a nice quadratic for revenue. My revenue function will be 75 minus 5x times 14,000 plus 800x. So I don't think that this is probably not going to be the tough part to FOIL that out, find the derivative. What I want to think about is what the restrictions on x are. I know that the number of tickets can be between 0 and 20,000, but that doesn't tell me my restrictions on my variable x. So I'm going to say that 0 is less than or equal to the number of tickets sold is less than or equal to 20,000. And then I want to figure out what that means for my variable x, like what are the boundaries for that? So if we sell 0 tickets, that would be 14,000 divided by 800. X would be negative 17.5. So if you have an X of negative 17.5, remember X was the price reductions. So this would actually be increasing the price by $5 that many times. So because it's the opposite sign, it would be a price increase. Like if you put in negative 17.5 into there, I'm just going to figure that out. That would give a price of like $162 a ticket. So they're saying if you charge that much, nobody will come. You'll have 0 sales. We know that that's probably not really accurate, but we're going with it for this question. And then if we had 20,000 sales, that's probably what we're more interested in, equals this 14,000 plus 800x. Bring that 14,000 over. Now I have 6,000 equals 800x. So what would x be? That would be 7.5. If you increase decrease the price, 7.5 times, like make that price decrease by that much, you're selling out. You're not going to have any more tickets to sell, so there's no sense lowering the price because you can't fit any more people. So that's going to be our domain for x. X can be negative. We can include that, the negative 17.5, because it's not It's not something that can't go into the negatives. It's not like a time, or X is not the number of tickets. You can't sell a negative number of tickets, but X is just how many times I'm increasing or decreasing the price. And that would just be a really big price increase because of the opposite sign there. So X is going to be between negative 17.5 and 7.5. So if I FOIL this all out, I get 105,000, big numbers here, I need to use a calculator, plus 60,000 X, minus 70,000 X, minus, some of these I should not be using a calculator for, 4,000 X squared. So I've got negative 4,000 X squared minus 10,000 X plus $105,000. So the derivative would be negative 8,000 X minus 10,000. And where does the derivative equal 0? That would be when 8,000 X equals negative 10,000. And that would be negative 1.25. So we would want to check what's the revenue at negative 17.5, what's the revenue at 7.5, and what's the revenue, and these are both going to be 0. Remember that this is, oh, pardon me, that one is going to be 0. So this would be if you sell 0 tickets. That's going to be a 0 for sure. This one we don't know. This I do have to calculate. So if that's 7.5, and then I'm going to check R at negative 1.25, which was my critical value that I found there. So going up into our revenue equation, I will put all of these in and figure out what the optimum one is. Okay, so I have calculated these guys, and we do see that this is the best or optimum value. We can maybe just squeeze a slide in here to have a bit of room. And remember that X being equal to negative 1.25, what that means is that that's the number of price decreases. The number of $5 price decreases. So we can figure out that the price was 75 minus 5X, and the sales was 14,000 plus, how much was it that it went up each time? That was plus 800X. So by putting in negative 1.25, 75 minus 5 times negative 1.25, we actually get that the price should increase. The best price would be $82.50. So they actually, I think that it's $82.50. I'm doing that in my head. No, $81.25. So here, $81.25 is going to be the best price. And you're actually increasing the price a little bit, which will reduce the number of sales, because I'm going to have plus 800 times that negative, but it actually will even out. So therefore, the best ticket price is 81.25 to maximize revenue.